Aloha BIOCHEM. In this final Chapter 2 video, we discuss the periodic trends. So, we'll cover section 2.8 this time, periodic trends. Our last video was rather long, and this one hopefully will make up for that by being shorter. Here are the notes. There are three periodic trends that we need to discuss, but the third one will wait until chapter 4. So really the first two, the atomic radius and the ionization energy, need to be discussed now. The good news is that all three of these are related, and if you understand one of them, it will help us understand the other two. So what we'll do is we'll talk more about the atomic radius, make sure we understand why certain atoms are bigger and other ones are smaller, and once we get that, I think you'll more easily get the ionization energy and the electronegativity. So what we mean by periodic trends are, when you look at the periodic table, here's a periodic table, none of the elements are listed, but you can see the shape. Some of these atoms are bigger and other ones are smaller, and there's a certain trend that as you get closer to this bottom left-hand corner, those atoms have a larger atomic radius. You see the atomic radius is the pink arrows. So as you go to this bottom left-hand corner, those are the biggest atoms, and as you get further away from the bottom left-hand corner, those are the smallest atoms. So that's the trend in atomic radius. There are a couple of other trends on here that we'll mention, but let's stick with the atomic radius for now. Another way to view the trend is this interesting looking periodic table right here. You can see this is a three-dimensional plot, and each atom, the size of the bar indicates how large its atomic radius is. So this is the largest atom right here, represented, rubidium. Although this periodic table only lists the first 5 periods, but you can see the trend that as you get closer to the left-hand corner, those are the biggest atoms. And as you get closer to the right-hand corner, those are the smallest atoms. Okay. Now, part of this trend is intuitive, and part of it is not intuitive. It's probably not too much of a stretch to see that as you go down a column, the atoms get larger and larger. Because, there are more electrons in the atom. You're getting to larger and larger shells occupied by the electrons. And so the atom gets bigger and bigger. But maybe a less intuitive part of the trend is that as you go to the right across a period, the atoms actually get smaller and smaller. So look at lithium, for example. Its atomic radius is 152 picometers. Beryllium gets smaller, and then boron gets even smaller, and basically it gets smaller and smaller and smaller. And that happens on pretty much every single period, with a few exceptions. So why do atoms get smaller as you go across a period? I thought carbon was element number 6 and boron's element number 5. I would think as you go, further along in the atomic number, the atoms would get bigger. You're talking about more protons, more neutrons, and more electrons. So why does the radius actually get smaller, as we can see here? Well, there's a very good reason for that, and let's discuss this a little bit further in the notes. So the atomic radius, first of all, if you need reminding, it's the distance from the center of the atom to the edge of the electron cloud. So if we're looking at that lithium atom right here, you remember we drew a model of the lithium atom in the lecture a couple videos ago. It's the distance from the center of the atom to the edge of the electron cloud, and that's 152 picometers. All right. Now, I've listed the atomic radius for several atoms, lithium, beryllium, boron, and then sodium, magnesium, aluminum, and then potassium and calcium. So these you'll find on the periodic table right here. So lithium, beryllium, boron, sodium, magnesium, aluminum, and then potassium and calcium. You see those ones right here, those 6 right here, and then these 2. So I think if we just understand the trend within these 2, you'll see why the trend works in general. So going back to the notes, so you have these 6 atoms, and then those 2, they're all next to each other on the periodic table. And next to the element, I've written the electron configuration. So lithium is element number 3. Its electron configuration is 1s2, 2s1. I'll remind you how to get that. So lithium is right here, right here. So to get the electron configuration for lithium, you go across the first period, 1s2, and then 2s1. It's the first spot in the 2s section, so 2s1. So 1s2, 2s1. That's lithium. And then beryllium is right there. It would be 1s2, 2s2. And then boron over here would be 1s2, 2s2, 2p1. So here's lithium, beryllium, and boron, and you can see their corresponding electron configurations. And next to all of these atoms, I've written their electron configurations. And in addition, the models of the atoms are also drawn. So looking at the model for lithium, we see that it's element number 3, so there must be 3 protons in the nucleus. And then those 3 electrons that surround the nucleus in the electron cloud, we can see where they are using the electron configuration. You see 2 of them are in the inner shell, that shell number 1, which is the 1s orbital. Those 2 electrons are in the 1s orbital. And then that 1 electron is in the outer second shell in the 2s orbital. Okay, so there's 1 outer electron. Now, let's go over to beryllium. Beryllium is right next to lithium. It's element number 4. So it has 4 protons in the nucleus and also 4 electrons around it. Now, there are 2 electrons in the inner shell and then 2 electrons, 2 valence electrons in the outer shell. So why is it that beryllium has a smaller radius than lithium? Well, think about what the radius is. Again, the radius is the distance from the center of the atom to the edge of the electron cloud. So basically, however far these valence electrons go would be the edge of the electron cloud, and that distance right here would be the atomic radius. Now, the reason that lithium's single valence electron goes further away than beryllium's 2 valence electrons do, you see these 2 valence electrons only extend out from the center of the nucleus to the edge of the electron cloud 112 picometers versus lithium's, which goes all the way out to 152 picometers, way out there sometimes. The reason these 2 are held more close to the nucleus is because they feel the power of that positive 4 charge in the nucleus. So this +4 nucleus is pulling in this electron and that electron. They both experience a +4 charge, whereas this one over here, this valence electron, is only experiencing a +3 charge. So it's not held as tightly because the nucleus doesn't have as large of a positive charge. And so that's why beryllium is smaller, because the powerful +4 charge pulls in those valence electrons tighter. And if you go over to boron, the trend continues. You see boron has 3 valence electrons in a couple of different types of orbitals, but there are 3 outer electrons, and these 3 electrons feel the effect of a +5 charge. And so they're pulled in even tighter than beryllium's, which feel the +4 charge. These guys feel the +5 charge, and so they're pulled in even tighter, and boron has a smaller atomic radius. So you see, that explains, hopefully clearly, why atoms get smaller as you go to the right across a period. And going back to this three-dimensional table, you can see as you go to the right, the outer valence electrons are experiencing a larger and larger positive charge in the nucleus, and so they're pulled in tighter and tighter, and that happens along every single row. Now what about as you go down the column? Well, this is more clear. Let's take a look at the models. So going from lithium to sodium, sodium is right below lithium. I'll remind you, lithium and sodium and potassium are all in the same column. You see lithium is 152 picometers atomic radius, and then sodium is bigger, and then potassium's is bigger. Well, as you go down a column, the atom gains more shells. And so lithium has electrons in the first and second shell, but sodium, with many more electrons than lithium, will end up occupying the third shell. And potassium even has an electron in the fourth shell. So the shells get bigger and bigger as you go, as you go down a column. And so that's why the atoms get bigger and bigger. And this happens for every column. You can look at the beryllium column. So here's the alkali metals, and here are the alkaline earth metals. And you can see the alkali metals get larger and larger going down, and so do the alkaline earth metals, and so do all of them, the halogens, the noble gases, and so on. And so the atoms get bigger as you go down a column and as you go to the left. They get smaller as you go up a column and to the right. So this is the small corner, and that's the big corner. And going here to this representation, maybe this is helpful. If you look at the pink arrows, they represent the atomic radius getting bigger, and this is the big corner, and that's the small corner. So sometimes there are test questions which state, say for instance, here let's look at a periodic table. Suppose you're asked, which is the larger of the two atoms, sulfur or phosphorus? Sulfur or phosphorus? Which one is the larger atom? Well, the answer would be phosphorus because it's closer to the big corner. Okay, now which one would be the larger of the two atoms, chlorine or bromine? Chlorine or bromine? Well, bromine would be larger because it's closer to the big corner. Every once in a while you might see a more tricky question, which is the larger of the two atoms? Boron or chlorine? Boron or chlorine? I would probably have difficulty just knowing the answer because I can't tell which one is closer to the big corner. So hopefully there would be a choice which says too difficult to decide. And sometimes you'll see tricky questions like that where one of the choices is it's too difficult to decide. Usually the answer is clear, like if it's between sulfur and phosphorus, phosphorus is the bigger one because it's clearly closer to the big corner. Okay, now the other trend that we discuss, which is closely related to the atomic radius, is the ionization energy. So the ionization energy, let's see what this is. This is the amount of energy to remove an electron. So the amount of energy that it costs to remove an electron from an atom. Now, I have a typo here. This should say smaller. Smaller atoms means it's more difficult to remove the electron. Dagnabbit, another typo. I hate typos. So smaller atoms, the electron is more difficult to remove. So looking at these right here, you see out of these that we've drawn models for, boron is the smallest atom, and that one would have the highest ionization energy. It would be more difficult to remove an electron from boron than it would be for potassium. Now, the reason is because this electron is being held very close to the nucleus, and it's very difficult to remove electrons that are held so close to the nucleus. The way I like to think about this is through an analogy, something that happened to my mother and one of my aunts. They were in Atlantic City, and they got mobbed one time outside a casino, and my aunt had recently won a few $1,000s. This was back in the 80s, so a few $1,000s was a big deal back then. It's still a big deal today, but a much bigger deal back then. And so she just won a few $1,000s, and she had this cash in her purse, and somebody must have seen her put the cash in her purse, and when they went outside the casino, they all of a sudden got mobbed by a bunch of people, started shuffling around them, and my mom and my aunt knew something funny was going on, so she held that purse really close to her, but no matter how tightly she held it, eventually somebody ripped it out while they were being mobbed, and there was no punching or anything, but just the having 20 or 30 people all of a sudden come at you in a big shuffle of crowd. She lost her purse and lost all that money. So, what do you think would be easier to take? Boron, one of boron's electrons that are very close, or maybe potassium's electron, which is like, holding your purse way out here. Here you go. You take my money. If you hold a purse like way out, it would be easy for somebody to take that. But if you hold your purse tightly, it's more difficult to take. It can still be done. You can still remove boron's electrons, but it takes more energy to do that. It's much easier to remove an electron when it's way out, far away from the nucleus. And the valence electrons are the ones that are always removed first. Okay, so that's what ionization energy is. It's a measure of the amount of difficulty for removing an electron from an atom. Okay, so taking a look at all of these atoms, the electron, the smallest atoms are holding their electrons more tightly to the nucleus, and so they are more difficult to remove. As you get to larger and larger atoms, those valence electrons are held more loosely, and so the ionization energy is smaller. It's easier to remove. Okay, and as you go down a column, it gets easier to remove an electron. The atoms get bigger. So the bigger the atom, the easier it is. So I made that typo. Sorry about that. All right. Now, in the next chapter, actually in chapter 4, we will discuss a third related trend. It's very closely related. And if you understand the atomic radius trend, then you understand the electronegativity trend. And this is kind of opposite to the ionization energy. The electronegativity measures the tendency of an atom to attract electrons. So rather than losing an electron, what about gaining an electron. That's electronegativity, and we'll talk about that another time. Okay, so you get these two trends in this chapter. For atomic radius, these are the large atoms, those are the small atoms, and for ionization energy, this is where the highest ionization energy is, where the small atoms are, and that's where the smallest ionization energy is, where the large atoms are. All right, well, that concludes our chapter 2. So in our next video, we will start chapter 3 on ionic compounds. So stay tuned for that. Aloha.